Hello, this is Richard Hammock's Calculus 1. We are in part 4 of the course on applications of derivatives. This is lecture 36b on Newton's method. Newton's method is a method of applying derivatives to the algebraic problem of solving equations. It was invented by Isaac Newton, who was one of the inventors of calculus, and he used it to solve equations where factoring or other methods of isolating the variable didn't work. Newton's method is based on linear approximation, which we introduced in lecture 36a, and I'll remind you of how it works. We have a function y equals f of x, and we pick a value of a for x. We take f of a, we get a point up here on the graph of the equation, and there's a tangent line there. And that tangent line is the graph of a linear function L of x that has expression f of a plus f prime of a times x minus a. Today we will be especially concerned with where this linear function crosses the x-axis. What is its x-intercept? And it's easy to check that that x-intercept right there is x equals a minus f of a over f prime of a. And maybe the quickest way to see that is to take this number and plug it into x in L of x and check that you get y equals 0. Check that L of x evaluates to 0. So we're plugging in this number to x, and where is the other x? It's right there. So you plug in a minus f of a over f prime of a for x right there. And the first thing that happens is you subtract off an a. So that a right there is gone. So in parentheses, this expression is minus f of a over f prime of a. You're multiplying that by f prime of a. So the f prime of a on the bottom cancels, and you're left with negative f of a. This entire expression right here is negative f of a. Add it to that f of a, and you get 0. So this point right there, that x-intercept, is the number a minus f of a over f prime of a. And keep that in mind, because that's the heart of Newton's method. And here's how it works. Newton's method is designed to solve an equation that has the form f of x equals 0. So some expression involving x set equal to 0. And Newton's method will find the solutions x that make f of x equal to 0. And here's how it works. Think about the graph of y equals f of x. You're looking for the values of x that make f of x equal 0, and those are going to be the x-intercepts. So right here, there's a solution, whatever x that is, that makes f of x equal 0. And we want to find that solution. We want to solve this equation, so we're going to find that solution. And here's how Newton's method works. First of all, you make an educated guess as to what that solution is. And let's call your guess a sub 1. Now, that's very unlikely to be the actual solution. It might be pretty close if it was a good guess, but it's not going to be the solution. What Newton's method is going to do is to move that guess, a sub 1, closer and closer and closer to the solution. And it works like this. You guess at a solution, a sub 1. You take that a sub 1, go up to the graph, and then look at the linear approximation at that point. This tangent line, and what you want to think about is what is its x-intercept right here? That's closer to the solution. Well, that x-intercept is given by this expression with a1 plugged in for a. So let's call that point right there a sub 2, where that linear approximation has an x-intercept. And by our expression up here, a sub 2 is our a sub 1 value minus f of a sub 1 minus f prime of a sub 1. So that a sub 2, it's closer to the solution than a sub 1 was, but it's not the solution. What do? You apply this exact same process to a sub 2. You look at the linear approximation at a sub 2, and you think about what is its x-intercept. Call that x-intercept a sub 3. How would you get it? Well, it's the linear approximation at a sub 2, so you would plug a sub 2 in for a in this formula. Your a sub 3 would be a sub 2 minus f of a sub 2 over f prime of a sub 2. And then you keep going. You next have an a sub 4 right there. You take the linear approximation at a sub 3, and there's an a sub 4, and you would get that a sub 4 by plugging in a sub 3 into the coordinate, into the equation for the x-intercept of that linear approximation. So a sub 4 is going to be a sub 3 minus f of a sub 3 over f prime of a sub 3. Now you keep going. You carry that process out, and you're getting a sequence of numbers, a1, a2, a3, a4, a5, and so on, and they're getting closer and closer to that solution. For large n, the number an is a very good approximation to a solution. And in practice, you'll find that if your guess is good, you might get a solution that's accurate to 6 or 8 or 10 decimal places by about a sub 4, a sub 5, a sub 6, something like that. And we'll see that in our examples. Let's do an example. I've got Newton's method right here for reference. Our example will solve the equation x cubed minus x plus 1 equals 0. We'll find the values of x that make this equation true. And notice that this has the expression f of x equals 0, where all of this is f of x on the left. And that's exactly the kind of equation that Newton's method is designed to solve. So let's see. Our first step is to make a guess at what a solution would be. And for that, you might want to sketch a graph of the function. You can use your graphing techniques, increase, decrease, concavity, and so on, to get a rough sketch of f of x. And this particular f of x looks something like this. And you can see that it has x-intercept right there, somewhere between -1 and -2. And that x-intercept is going to be the solution, the x that gives you f of x equals 0. So we're going to make a guess as to what that should be, and that's between -1 and -2. So let's make our guess right in the middle of those two numbers. A sub 1 is -1.5. That's our guess at the solution. Now the actual solution looks like it might be a little bit to the right of that, but that's our guess. So in Newton's method, the first thing that you need to do is work out this expression that gives you a sub n plus 1 from the previous term a sub n. A sub n plus 1 equals an minus f of an over f prime of an. And let's work that out for this particular f of x, the x cubed minus x plus 1. We get an minus, then on the top of the fraction, f of a sub n. You're just plugging in a sub n to f, so that's a sub n cubed minus a sub n plus 1. And it's divided by f prime of a sub n. And let's see, f prime would be 3x squared minus 1. So that's 3 a sub n squared minus 1. So this is the expression that we're going to use to get a sub n plus 1 when we already have a sub n value. So let's get started. We'll organize our work on a table where each row will give a value of a sub n. And we already have our first guess, a sub 1, it's -1.5. So we're going to put that down right there. And the next thing we need to do is to calculate a sub 2. A sub 2 is going to be a sub 1 minus f of a sub 1 over f prime of a sub 1, where a sub 1 is negative 1.5. So in other words, you're plugging negative 1.5 in for a sub n in this expression. And you'd want to use a calculator for this. You'd get negative 1.5 minus the expression negative 1.5 cubed minus 1.5 plus 1 divided by 3 times minus 1.5 squared minus 1. You'd calculate that, and that's going to give you your a sub 1 plus 1, or your a sub 2. And if you do that on a calculator, you get a sub 2 equals negative 1.3478268. We're truncating some values there. We're just doing this to, 8 decimal places. So there's a sub 2. And you'll notice that is to the right of 1.5. So we're marching a little bit closer to that solution. But we've got to keep going. Next, we're going to calculate a sub 3. And to do that, you would take this a sub 2 and plug it into this expression. You plug in this number a sub 2 right in here, 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 and there. You probably want to use a memory feature of your calculator to do this, but when you do it, you get a value of a sub 2 plus 1, or a sub 3, which is this number. And then you have to calculate a sub 4. And to do that, you take this a sub 3, and you plug it in for a sub n in this expression. You work it out just like you did before. You'll get a sub 4 equals negative 1.32471817. Iterate again, plug in a sub 4 into our expression here to get a sub 5. A sub 5 works out to be this. And look, you can see you're stabilizing somewhere around negative 1.32471. You get some difference out here, but a sub 4 and a sub 5, they're really close together. They are very close to this actual solution to this equation. Let's do one more. We'll take a sub 5, we'll plug it into our iterative expression here to get a sub 5 plus 1, or a sub 6. And doing so, I did this on a calculator, I got this number for a sub 6. And you'll notice that the number for a sub 5 and a sub 6, they agree completely. Now, it actually turns out that they are a little different, but the difference happens further out than 8 decimal places. So you can see here that if you kept doing this, you just get this number over and over and over again. Theoretically, you'd be marching in closer and closer to the actual solution, but we've exceeded the accuracy of our calculator at this point. So we're going to stop here, and we can see that our solution to 8 decimal places to f of x is x equals negative 1.324711795. We'll just use this number that we got both for a sub 5 and a sub 6. So there we go. We've found a solution at least to 8 decimal places of this equation. And if you want more accuracy, you take it further, calculate A7, A8, A9, and use a calculator that has greater accuracy. But this is going to be good enough for us.
For our next example, let's solve the equation sine of x equals x squared. We want to find its solutions. Just looking at this, you can probably see right off the bat one solution that's easy to find. It's x equals 0. Sine of 0 equals 0, and 0 squared equals 0. So x equals 0 solves the equation. That's one obvious solution. We got that not by using Newton's method or any other technique, but just by looking at the equation. But you might wonder, are there other solutions? Think about the graph of x squared, shown here, and the graph of sine of x, shown here. You can see that these two graphs intersect at 2 points. There are 2 x values here And also it looks like one here where sine of x equals x squared. And the one that's right here, that's x equals 0, where the graphs cross. That was our obvious solution. What about this other solution that's right there? At some number, it looks like it's slightly less than 1. You get sine of x equals x squared. Let's see if we can find that solution. We can use Newton's method to find it. And before we get started, I want to point out that if you tried to solve this equation, to find this other solution by algebraic techniques or trigonometric techniques, maybe take the sine inverse of both sides and so on, you'd run into trouble. It would be impossible to isolate the x. You couldn't get it as x equals something. You're always going to have an x on both sides. So familiar techniques of solving equations are going to fail us for solving this equation for the solution here. So let's apply Newton's method. The first thing we want to do in Newton's method is to make a guess at this solution. And how about we make a guess of a1 equals the number 1? That's pretty close to, it looks like that's pretty close to the actual solution. So that's our first step in Newton's method. a1 equals 1. In applying Newton's method, we have to apply it to an equation of the form f of x equals 0. That's the way Newton's method is set up. But notice we don't have that here. It's sine of x equals x squared, not f of x equals 0. To apply Newton's method, the first thing we would do is write this equation in the form to which Newton's method applies, f of x equals 0. And you can get that really easily by subtracting an x squared from both sides. So rather than solving sine of x equals x squared, let's solve an equivalent equation, sine of x minus x squared equals 0. So that's of the form f of x equals 0, where f of x is sine of x minus x squared. And we can apply Newton's method to that. Now remember, Newton's method works by taking a guess at the solution and getting a better approximation to the solution from that guess using linear approximation. And the way it works is once you have an a sub n, like this a sub 1, you can find a sub n plus 1, the next approximation, as a sub n minus f of a sub n over f prime of a sub n. And let's work out what this would be. Bring over the a sub n. F of a sub n would be this equation with a sub n plugged into it. That's sine of a sub n minus a sub n squared. And we divide by f prime of a sub n. And look at f prime. It's cosine of x minus 2x. So f prime of a sub n on the denominator would be cosine of a sub n minus 2 times a sub n. So this equation is saying whenever you have an a sub n, you can find the next approximation, the better approximation, a sub n plus 1, by plugging in a sub n to this expression. As we did in the previous problem, let's organize our work with the table for the a sub n values. We started off with our initial guess, a sub 1 equals 1. And as you can see, that's wrong, but only slightly so. The next step would be to plug in a sub 1 into this expression to get a sub 1 plus 1, or a sub 2, and plugging into 1 into the sine and the cosine and squaring it here and times 2 there and so on, and making sure your calculator is in radian mode. Plugging in 1 for all the a sub n's, you will get, if you try this, your a sub 2 is 0.89139959. And this is to 7 decimal places. Of course, these trail off after that, but let's just work with 7 decimal places. round off at the 8th decimal place. So that's a sub 2. And notice 8.9, that's a little less than 1. So you're a little closer to this unknown solution. You want to get even better, so you need to compute a sub 3. You take this number and you plug it in for the a sub n's in these 5 places, and you'll get a sub 2 plus 1, which is a sub 3. And plugging in this number here, you'll find that your a sub 3 is this number to 7 decimal places. It's a little bit smaller than what we got before, so you can see you're kind of marching closer to that question mark. Next, do a sub 4. Take this a sub 3, plug it in for the a sub n's, and you'll get a sub 3 plus 1, or a sub 4. You'll find that a sub 4 is this. And iterate again. Take this a sub 4, plug it in for the a sub n's here, and you'll get a sub 4 plus 1, or a sub 5. And I worked this out on my calculator, and I got this value. And notice that to 7 decimal places, that's exactly the same as a sub 4. Now, there was a change, but it happened after the 7th decimal place. So our point of view here is that 7 decimal places is good enough to get a very good approximation to the solution. So we actually picked up 2 solutions to this equation, sine x equals x. They are the obvious one, x equals 0, and also x is approximately equal to 0.876762, which is right there. If you want more accuracy, just take it to A6, A7, A8, and so on. By letting a sub n get bigger and bigger and bigger, the n get bigger and bigger and bigger, you get a closer and closer approximation to the solution. But we got it to 7 decimal places right here, so we're going to stop there. So there we go. Our second example, we found all the solutions to sine x equals x squared.
As I said before, Newton's method is not something that you'll use every day. In fact, you may never use it at all. And the reason is that today we have software packages that do things like solve equations, among other things. And these packages employ methods like Newton's method or similar methods. Still, I think it's good to know what's going on under the hood when you use them. We'll wrap this up with a few final remarks about Newton's method.
I do want to point out some things that can go wrong that you might want to watch out for. First of all, you might be solving an equation like the one graphed here, and maybe at some iteration you get an a sub n that's like this, where the tangent line is equal to 0, or has slope 0, and that's not going to cross the x-axis at all. And in fact, if you think about the formula for a sub n plus 1, it's dividing by an f prime of a sub n, so you're going to divide by 0 there. And at that point, the program just crashes. So that's a pitfall. Another thing that could happen in Newton's method that would go wrong is you might have something like this f of x, and you're trying to find the solution. And actually, you can see the solution right there is x equals 0. And maybe you make a guess of a1 right there. And to find a2, you use linear approximation. You go up to the graph, you do the tangent line. It hits right there. That's a sub 2. And then you want to find a sub 3, so you take the linear approximation at a sub 2. And doing that, you go here, look at the tangent line, and it got right back to a sub 1. So that's actually what you get for a sub 3. You applied linear approximation at a sub 2, you're back here, so a sub 3 is equal to a sub 1. In the next iteration, you want to find a sub 4. You take linear approximation at a sub 3, you look at where it crosses right there where a sub 2 was, and that's a sub 4. And at this point, you can see that Your approximations, so-called approximations to the solution, are going like a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6. They're just bouncing back and forth, and they're never converging to the solution of 0. This is an infinite loop. Well, that's something that could go wrong too. So you can see here that Newton's method is a little bit of an art. You have to sort of know what you're doing when you're using it and be alert for these pitfalls. Another thing you'd have to watch out for is this. Suppose you had a function like this one, where f of x equals 0 has no solutions. This graph never crosses the x-axis. And imagine that you just blindly applied Newton's method to find a solution. You made a guess of a sub 1, you got to a sub 2, you did linear approximation again, a sub 3 is there, then a sub 4 is here, and then you find a sub 5, it's right there. Well, those numbers are just bouncing around randomly almost. They're never converging to a solution because there is no solution. So you might file this one into the maxim garbage in, garbage out. You applied the program to an equation that has no solution, and you should expect garbage. Another pitfall is this. Suppose you have an equation that does have solutions, and maybe you're looking for this solution right here. You want that solution, and you go, okay, well, I'll take a guess that's pretty close to that, like this a sub 1, and you're trying to get this solution, but look at what linear approximation does. It takes you down here. You cross the x-axis right there, and you can see that when you apply Newton's method with a sub 1 as your starting point, you're going to get this solution. You wanted this solution, but you're going to get this solution. So you might file this under uncritical use of Newton's method. It's an art. You have to use it in the right way and know what you're doing when you use it.
In conclusion, we have Newton's method, a method of applying derivatives to the problem of solving equations. We create a sequence of numbers, a1, a2, a3, a4, that get closer and closer to that solution. You might say the solution equals the limit as n approaches infinity of a sub n. Now take note of that limit. It's a fact that limits arise often in calculus, and not just in the definition of the derivatives. You're going to see lots of limits, especially in calculus 2. Coming up next, we'll introduce L'Hopital's rule, and it is a method of applying derivatives to the problem of evaluating limits. I'll see you then, and goodbye.